All right. So this is the last lecture. We've reached the end of the semester. As I said, there will be a problem-solving session right after this in the physics department until 11:55. All right. So today we're going to be talking about time reversal and lattice translations. But as usual, I start with a review of the last lecture. We talked about the connection between symmetry transformations, conservation laws, and degeneracies. An important statement from part 1 of the course that I reminded you was that if you have two self-adjoint operator, Hermitian operator that commute, two observables that commute, the eigenkets of B, so A and B commute, if B has no degeneracies, then eigenkets of B are eigenkets of A as well. But if B has degeneracies, the eigenkets of A are some superpositions of degenerate eigenkets of B. Good? That's semi-clear. I'll give an example. For example, consider free particle with free particle. Hamiltonian momentum commute. The eigenkets of P are, oh, never mind. Change my mind. The eigenkets of P, we're going to write them as P prime kets. Eigenkets of P doesn't have degeneracies, therefore eigenkets of P are going to be eigenkets of Hamiltonian as well. However, Hamiltonian has degeneracies, so not all eigenkets of the Hamiltonian are eigenkets of P. For instance, here is an eigenket of Hamiltonian, right? You can see explicitly. However, it's not an eigenket of P. Only the two eigenkets of Hamiltonian that are also eigenkets of P correspond to either C1 equals 0 or C2 equals 0. Right? This is just a trivial example of this general principle. Questions? All right, we talked about parity or space inversions. This is a transformation that stands in 3 dimensions, x, y, and z to minus x minus y minus z. So the vector x to minus vector x. We saw that it changes right-hand rule to the left-hand rule. In quantum mechanics, this transformation, so first observation is that this transformation applied twice gives you back identity. So it forms a group. The group is Z2. In quantum mechanics, this transformation is represented by a unitary on the Hilbert space. That unitary will be represented by some operator pi. And we saw that, well, it's pretty clear that pi x, so first of all, it's clear that because it's unitary, pi dagger is pi minus 1. And because pi squared equals 1, it means that, what does it mean? It means this. Right? Therefore, if you want to send an operator A, if you look at the transformation of an operator A in the Hamiltonian, Heisenberg picture under this unitary transformation, I sometimes write it like this. I can also equally write it as this. They're all equal. Good. All right. So, or sometimes I put the dagger here. You see all these expressions, they're all the same, right? Because it's Z2. The operator is equal to its minus, inverse equal to its dagger. Is simultaneously self-adjoint, Hermitian, and unitary. So pi x pi is minus x by the virtue of the fact that it's a representation of this of parity, space inversion. From this, it follows that pi and x anti-commute. Good. We said that similarly, if you look at the action of parity on the p vector. P vector is, they also anti-commute. So we call these guys vectors that are odd under parity. We also said that there could have vectors, vector-looking things that are even under parity. Examples were angular momentum, orbital or spin. Yeah, we call these pseudo vectors. Similarly, we can have scalars. A true scalar is even under parity. Example would be L dot S, but S dot X is something that acts like a scalar under rotations. However, under parity, it is odd. It picks up a minus sign. We call that thing a pseudo scalar. Good? All right. Wave functions and parity. We talked about wave functions that are even parity, they should satisfy this property. If they are odd parity, they should be antisymmetric. Good. So this was just a review of the last lecture. Are there any questions? It's distracting. Everyone walks down the hallway. All right, so today we're going to talk about two other discrete transformations that we mentioned last time. One of them is time reversal. I'll have to first explain what it is. And then the other one is lattice translations. So let's talk about time reversal. Time reversal is a little bit of a misnomer. What it is the following. Let me describe it. Imagine you're watching a movie, right? Like a soccer game or American football game, more in the context. Somebody kicks a ball, right? And the ball is moving, right? You just see the ball move, like in a certain direction. This is where and it looks physical. It looks like it's correct. It's described by equations of motion. It's properly describing the motion. And F equal ma describes how it acts, how it evolves. Now you start watching the movie in reverse. The ball moves in the opposite direction. It still looks natural, still looks physical. So if this thing is sliding on the table in this direction, imagine there's no friction, right? This looks like it's physical. If it slides in the opposite direction, it still looks like physical. So what it means is that the equations of motion evolved forward in time. The solutions of F equal ma. Evolved backward in time are also solutions, right? This is not always the case. Give me an example. I'll really give you an example.
When you rewind a movie, it doesn't look the same.
Yeah. What would there be an example of such a thing? What's that? Diffusion, but like a simpler example. That's not, well, okay, that's a very tricky example. That's a correct example, but it's a very tricky one. Well, look at this. This, if you watch it in reverse, what would it look like? This was at rest, starts moving. That's nonsense. That never happens. So friction, in the presence of friction, that's a good example. Actually, falling under gravity, motion under gravity is a good example, but it's a tricky one because for other reasons. So in the presence of friction, it's no longer true. What is special about friction? Force that the object feels is proportional to its velocity, right? When you change the direction of time, you change sign of the velocity, right? Because velocity was dx dt. You just flip the sign of t. Now velocity or momentum is in the opposite direction. So the force, if the force is proportional to velocity, then the motion of the particle looks unnatural under a sign flip of time. Do you know any other forces that are proportional to velocity besides friction? What's that? Yeah, Lorentz force. if you have a particle moving in some background magnetic field, the force it feels is V cross B. This is exactly the right-hand rule. So if you have a particle moving in this direction, there's a magnetic field sticking out, right? You know the magnetic field is sticking out of the board, so it starts spinning this way. If you watch the movie in reverse, the charge of the particle is still the same, but the velocity is spinning in the opposite direction, which is in contradiction with the right-hand rule, because the right-hand rule is switched to left-hand rule. So that is not time reversal invariant, whereas force like F equal ma without any friction is time reversal invariant. Right? This might sound like sci-fi to talk about time reversal. It's what it is just is that under switching the sign of t, do you get a new solution to the equation of the motion? Good. So that's what time reversal is classically. Now, what is it? What is time reversal in quantum mechanics? It is a little bit tricky. Not very much, but it's a little bit. So here's the evolution of a wave function. You apply e to minus iht to some ket and look at the wave function, your favorite basis. For example, position basis. If you flip the sign of t, of course it's not invariant. These two are not equal. But something that you could easily convince yourself of is that if this take this wave function and expand it and energy eigenbasis. This is what it looks like. If you flip the sign of t, this minus becomes plus, but that is like taking complex conjugation. So if you take the complex conjugate of this guy as well, now this is a physical solution. So in quantum mechanics, if you have psi of x and t, psi of x minus t star is a solution. Now, if you are in a situation where the energy eigenkets are real, that system, those states of those systems show time reversal invariance, symmetry, right? Because if you flip the sign of this, this doesn't need to change. What's an example of such system? We saw examples of that. Think about it. All right. Time reversal squares to identity, right? In all the examples we were talking about, if you watch the movie in reverse and then watch it in reverse again, right? It will be back to identity. So it squares to. Any questions? Here's an important statement. There's something very, very special about time reversal invariance or time reversal transformation as opposed to other transformations we've talked about in this course. When we talked about symmetry transformation, we modeled them by unitaries. Why was that? Do you remember why? Because the probability to have the probability of having some ket alpha and finding it in some other ket beta is the overlap of alpha and beta squared. We would say it's a symmetry if you rotate, if you transform both alpha and beta, the probability doesn't change, right? Good, is that clear? So the probability for any physical transition going from some state to another state is the overlap of alpha beta. Any physical process should not change under symmetry transformation. The probability of its occurrence shouldn't change. So if you model symmetry transformation with unitaries, that's guaranteed. How? Well, alpha and beta are acted upon by a unitary. The overlap after the transformation is u dagger u sandwich in between alpha beta, but u dagger u is identity for unitaries, therefore the probabilities are preserved. However, you can instantly see that there is room for another possibility. It's possible that, so in this case, what is actually preserved is the amplitude. So beta alpha is equal to beta tilde alpha tilde. Right? For unitary transformation, this is true. However, if you have a symmetry transformation that does this, still the probabilities are preserved. Sounds very bizarre, but it's a possibility. Such a transformation is an anti-unitary. We'll define it. All the symmetries you know in physics, pretty much almost all of you guys, are going to be represented by unitaries, except for one. That is time reversal. That's going to be the anti-unitary. Now, if you do some fancier mathematical physics, you might find some more other anti-unitary stuff. But the example of an anti-unitary transformation that models a symmetry is time reversal. Everything else is unitary, pretty much. That's a little bit of a social. Yeah, that's not a rigorous statement. Is that stemming clear? If you have this after the transformation, you have this, the probabilities are still preserved. We will see that time reversal will prove that time reversal must satisfy this. It cannot be a unitary. We'll prove that in a bit, right? But before doing that, let me explain some subtleties regarding anti-unitaries. So let's explain what an anti-unitary is. It's something that even after working in physics for a very, very long time, you constantly find myself constantly confused. There is a notation you could use to help. So, all right, what is an anti-unitary? Let's start with this side. What is this? This is alpha tilde overlap with beta tilde star. Right? We usually write it this way because it's easier. Now we're gonna for parity we use pi as a representation. This is an operator. For time reversal, I'm gonna use this theta. It is almost a standard notation. Okay, good. So how does this transform? This becomes theta acts on the first vector. Oops, sorry. Sorry about that. So the transformation is this. Alpha tilde is theta alpha, and beta tilde is theta. Right? This means that you have theta alpha, and then you have theta star. Good? Or dagger. I should probably write dagger. Now, an anti-unitary is this weird thing that if you well, let me write it here. If you look at this, what you could do is that it's tempting to say what this is. If this were a unitary, we would just write it as theta dagger beta, right? This would be this. However, for an anti-unitary, you could write that, but you have to take the star of the whole thing. It's tricky, but I'll introduce a notation that will help, right? So is that clear? So what becomes is this. So from this line to the next line, this becomes theta dagger, which is also theta, beta, there is theta here, alpha. However, the whole thing picks a star. as I said, even after so many years in physics, every time I have to write this down and remind myself, unless I use a sort of some better notation. There's a notation that keeps track of it very nicely, right? Now, what is this? This is theta squared. Because theta dagger is theta. This is theta squared, which is identity. So this becomes beta alpha star, which is alpha beta, right? So you see the line of logic. This became alpha beta. This becomes beta alpha star. And the whole magic is here. If this were a unitary, a usual operator here, I would just write A dagger and B. But for an anti-unitary, you'll have to put a star. All right, let's pause here. Is that clear? Now, let me immediately tell you about it. This is a really horrible notation. It's awful to keep track of things like this. Let me tell you about the notation that's a little bit simpler. Now, this is a notation that's not exact, right? This is a notation that I think anyone who works with this stuff a lot will use. So previously what we were writing were things like this, right? And I was saying that it doesn't matter whether this could act on the right or it could act on the left. But if it's acting on the left, the dagger of it is acting on the left, right? So now let's use the notation. If it's acting on, to keep track of which direction it's acting, let's write it like this. If it's acting on B, you write AB. If it's acting on alpha, you write something like this, for example. Good? Is the notation clear? Now, instead of writing these ugly looking things, what you write is the following. You write, if you have a unitary, so for unitaries, you have the following property, that this is equal to U dagger alpha beta. Everyone is with me for this notation? For anti-unitaries, you have alpha theta beta is equal to theta dagger alpha beta star. Good? This is a notation I recommend. It's a lot easier than putting these brackets. All right. There's immediately something a little bit funny about anti-unitaries. They are not linear operators, they are anti-linear operators. So if you wish, this is the very definition of an anti-unitary. If you rotate alpha and beta by, if you apply an anti-unitary theta to alpha and beta, then the resulting overlap is initial overlap complex conjugate of it. And if you have a superposition of two vectors, theta you can bring it in, but you have to take the complex conjugation. That's such an operator is called an anti-linear. There's something very deep about the fact that we must use anti-linear and anti-unitaries to model time reversal. All right, I'm going to pause for questions. So is it clear what an anti-unitary is and what an anti-linear operator is? Anti-unitaries are anti-linear. And I'm going to explain next why we must use anti-unitaries. Just one second. to model time reversal. Yes.
Second line on the alpha, beta, or alpha.
Where second here? Here? Next line. Yeah, still alpha and beta is acting on the right. I'm describing the action of it on the right. What happens is that, okay, let me write this on the board. So an antilinear, what was a linear operator? A linear operator does the following. If you have A acting on C1 alpha plus C2 beta, these are complex numbers, right? This would be C1 A alpha plus C2 A beta, right? An antilinear operator, if you have that expression, you can bring this in. Once you pass it through the complex numbers, you'll have to take the complex conjugation. Oh, sorry. Theta here. That's what an antilinear is. So what does it mean? All right, let's do a little exercise. Imagine you have an antilinear operator, which is time reversal. Okay, acting on this ket, which was the eigenket of sigma x, right? What does it look like? How does it act? It's antilinear. These are real numbers. It's okay. I can bring them in. I end up with this, right? However, if you looked at eigenkets of sigma y, now you have an I here, there will be a sign here. Said differently, theta acting on I is minus I, theta. We'll see that now. Questions? Notice that the bracket notation we used, we sort of took advantage of the fact that we're not dealing with antilinear operators. We just kind of wrote, it was a very nice notation. The moment you're talking about antilinear operators, this other notation, which is still bracket, but it's a little bit better. It keeps track of things a little bit nicer. All right, any questions? Now, we are not next gonna argue or show why time reversal must be anti-unitary. All right. Let me first write the equations. First, write down. So what we're gonna do is this. We're gonna use unitaries to describe. We're gonna use unitaries to describe time reversal. Find a contradiction, and then see we can fix it if it's an anti-unitary. All right. So here's what it is. Consider some ket, evolve it in time by some delta t. So for example, this is t naught equals 0. Your ket is alpha of t, and then yeah, that's what your ket is, right? So this is a particle moving along this world line. This is t equals 0 was here, now it's here, and then this is the direction of time evolution is pushing you this way. Good. We're gonna do two things. First, we're gonna reverse time and then evolve forward. So the state was here. First, I'm going to do time reversal and then evolve in time. Compare it with evolving in opposite time and do time reversal, and you end up at the same place. Let me draw it here. Maybe. So the particle is moving this way, right? This was t not equals 0. Time reversal moves you in the like flips this, right? So this is where your particle is. There are two things we can do. We can first apply time reversal. That will bring it down here, right? And then move forward in time to end up here. Good. The other operation is you might say, I'm gonna first move forward in time and then apply time reversal. You do not end up in the same spot. What brings you back to the same spot is if you move backwards in time. So this is how much you move forward. If you move backwards in time by the same amount and then apply time reversal. There's something very special about time reversal here. Good? Right? Is that clear?
I have a question.
Yes.
The consider 1 minus IH delta T over H bar, that line,
This
we
one.
were just talking about where if you take the anti-unitary operator and you move it
Yeah. So very
a...
good. That's my point. For now, as I said, I'm gonna pretend I don't know anything about whether the operator is unitary or anti-unitary, right?
Oh, okay.
Right, and we're gonna find a contradiction and conclude that it must be an anti-unitary.
Okay, so you're suppressing that for okay.
Yeah.
Okay, thank you.
Well, I'm not. So far,
Well,
I haven't done anything incorrect. Everything I've done is okay. Right? This picture is sensible. The picture is sensible. And I'm just writing the equation that corresponds to it. So far.
Okay.
In the first part, I apply theta, time reversal first, then evolve forward in time. The second one, evolve backward in time and apply time reversal, you end up in the same place. Right? So that's just, this equation is just okay. From this, you learn that minus IH theta, right? This is identity, you can subtract it, has to be theta IH alpha. Right? This is also okay for now. We will get the wrong conclusion. We'll have the wrong conclusion if I can push I past this without flipping the sign. We'll do that in a second and see that gives the wrong conclusion. Is that clear?
Yes, thank you.
Of course. Of course, if it's an anti-linear, anti-unitary, pushing it on the other side, flips the sign, that's okay. The left-hand side and right-hand side look okay. But let me run this argument. But is it clear for now what this equation means? Okay, so imagine theta is a linear, we're a linear operator. Then you could take I out, bring the whole thing to left-hand side, and you would find that theta and H will have to anti-commute. This is what you would find. This means that if N is an energy eigenket, the time reversal of it is also an energy eigenket, however, with the opposite energy. That is nonsense. Why? Is it first? Let's see if this is clear. If you could take I out, well, you'll bring it to the left-hand side. Well, if you can take I out, you'll just cancel the i's, right? And you end up with minus H theta acting on alpha is theta H alpha, right? And now that would imply that if N alpha was an energy eigenkette of energy En, the time reverse version would have the exact opposite energy. That is nonsense in physics. Why is that? What is wrong if for every instability? Yes, that's correct. That's correct. If that were true, the system would have no low energy state. There won't be a vacuum. You could arbitrarily, like let's say a simple harmonic oscillator. You had the lowest energy state and higher energy states, right? But this, and then you had arbitrary high energy states. That means that if there would be kets in the Hilbert space that will have arbitrary low energy states, such a system is unstable. That makes no sense physically. You won't have a vacuum. Can you tell what goes wrong? What is a classical example of such a system? A system that has no lowest energy state. Just classical. Huh? You don't need such bad. So what's a simple harmonic oscillator classical? What's the potential? This. Right? So it has a vacuum. If you have a ball here, you roll it down, it will settle to the minimum. If you just flip the sign, it would be something like this. This doesn't have the lowest energy state. You push it and it just keeps rolling down, right? That's instability. This doesn't. This has states with arbitrary low energy. That's bad. The worst is if you have. Well, there's a simple. You say if you have this setup, you say, oh, you got the sign of the potential wrong. However, what we're finding here is that you have, if theta were a linear operator, you would have both arbitrary high energy states and low energy states. Arbitrary low energy states. That's nonsense. And the fix for it is very simple. As I advocated before, it's anti-linear. So you push this to this side and you pick a minus sign, there's no contradiction. As a matter of fact, like consider a free particle, right? As Hamiltonian as p squared over 2m. So if you apply time reversal, each factor of p picks up a minus sign, but the total p will be the total Hamiltonian will be unchanged, which means that theta and h commute, not anti-commute. Good. You also knew that had to be correct. We said asymmetry has to do with things that commute with the Hamiltonian, right? All right, questions? So this is only consistent if your operator is anti-linear. And of course, it commutes with the Hamiltonian, so it's a conserved charge. And then I described this already. Questions? All right, it takes some getting used to work with antilinears. It's a lot more natural if you use the notation that I was advocating, but if you insist on Saccharide notation, for what you find is something along these lines. So you could ask the following. You could ask, how does an antilinear, how do, if you have matrix elements of linear operators, how do the transformation work? So here's a matrix element of a linear operator. X, what do they call it? Called it X, right? Now what you want to do is you want to apply an antilinear here, an antilinear, anti-unitary here, and anti-unitary here, right? So this would be theta of alpha X, and this would be theta of beta dagger. It's not hard to argue that to find that that line is correct. So that's how it acts. You basically can bring this to the other side and swap in your alpha and beta. You'll have to take the dagger as well. Is that clear? How this works? Should I do it slower? Let me do it slower. So first, you get theta, x, theta, alpha, star. Now the star will bring alpha here, theta will be here, x will be dagger, theta and beta, right? You go into this. So I proved this for you. If it's a Hermitian operator, x and x dagger are the same, so you could just write the next line. Am I going fast or no? As I said, let me repeat this. The rule of thumb for at least for a couple of years for you guys until you find something fancier is that all symmetries are going to be unitaries unless they're time reversal. However, more generally, if you want to know what the story is, a symmetry, Wigner proved, must be, actually, we just also proved it pretty much, is either a unitary or an anti-unitary. And the only anti-unitary that you probably will ever deal with is time reversal, but you will deal with time reversal. What's an example of a system that doesn't have time reversal? A force of nature that doesn't have time reversal. Magnetic force, right? We saw that. Other forces usually do have it. Good. This is a very deep statement. If you ever go to more advanced field theory courses, you'll learn more about. It's a pretty deep statement about fundamental laws of nature. But anyway. All right. We can say again an operator. We could talk about whether Hermitian operator is even or odd under time reversal. Right? That just means this. Good. So an even operator on the time reversal, an even Hermitian operator on the time reversal will satisfy the first equation, or the and then odd one will satisfy the second equation. If you take the expectation values, they will transform this way. No surprises here. All right, based on these definitions, momentum is odd under time reversal. Position is even. You knew that, right? Even in classical physics, you knew that, right? So for a second, remember that this was your 2 plus 1 dimension. This is the setup. Parity is a transformation that keeps time the same, flips the sign of space. Time reversal is the transformation that flips the sign of t, but x, y, and z are the same. Good? So now momentum, what is it? M dx dt. You see how things transform. At x. Under parity, both of them will switch signs. So under parity, both of the two operators will end up being parity odd. Under time reversal, this is parity even. This is under time reversal. This is time reversal even. This is time reversal odd. No surprises here. These equations are the quantum versions thereof. For those of you guys who know a little bit about relativity, I encourage you guys to think about multiplying these two operators and playing around with it. Okay. One more thing. Importantly, in quantum mechanics, for particles, right, the spatial part of the wave function, we had this crucial identity. The commutator of x and p is IH bar Kronecker delta, right? That is preserved. These next few lines of algebra, it's pretty straightforward algebra, could follow it step by step. What this argument shows is that the only if this tells you that the fact that time reversal is anti-linear or anti-unitary means that that commutation relation is preserved. If time reversal was not anti-unitary, it were unitary, that commutation relation would be wrong. This is very crucial. This is another aspect of what I was just discussing, right? Like from this, you could also conclude that as an argument, you could conclude that time reversal has to be anti-unitary. Similarly, the same is true for spin, angular momentum, orbital or spin. I'm not going to go over it. It's just line by line. It's pretty straightforward algebra. Questions? So what I've not included, for the sake of time, is a discussion of how the wave functions transform under time reversal. We did the exact same. So it just, if I'm drawing analogies, parallels between parity, we described how operators ended up being parity, even, odd. We listed them. And then at the end, we just had one slide about how the wave functions transform under it. And that was just included from the transformation of the operators. Here for time reversal, we did the same, except that I just leave it to you guys to figure out, based on these equations, what is parity, what is time reversal even, time reversal odd, how the wave functions transform under it. There's really no magic. It's just writing down the expression. You could read it also in Sakura. Questions? In the last 25 minutes of this course, I will go over a last discrete transformation called lattice translations. This is going to be unitarily represented. But it's an example of a discrete symmetry, which is not Z2. All right, but let me pause one last time here. Are there questions about time reversal or parity? Both of them are groups, and the group is Z2. What does Z2 mean? So there are two transformations in this group. There are two elements of the group. If you multiply one by one, identity by identity is identity. Identity and time reversal, that's time reversal, it's obvious, right? Time reversal and time reversal, what is that? Oh no, you know this. What's that? Identity. Identity, yes, please. Okay. From this, you learn that theta minus 1 is, so there's an inverse. This is Z2. All right. Next, we're going to talk about different discrete transformation. This discrete transformation, let me I don't know why I like this. So we talked about translation in space, right? This was a particle in space, and I could just translate it in space by some real parameter in this direction. Let's say it's one dimension. Oh, people on Zoom don't see this. Anyway, I had a particle that I was translating in space. Imagine, for some reason, the reason being that the particle is confined to a lattice, you can't continuously translate it, but the particle is either here or hops. So here's the lattice, right? The particle could be sitting here. There's nothing in between. There's a lattice size. It could hop here. It could hop here. Hop here, right? These are discrete translations, right? This is also a group. It's actually a subgroup of translations, but it's discrete. The group is Z. Good. Integers. The multiplication of the group is addition. And the identity of the group is 0. Addition by 0. All right. So if I have a lattice, right? How do you make sure that the particle is confined to move on a lattice? Imagine I have a potential like this. Oops. I have a, how am I going to draw this? Yeah. Yeah, I have a potential. Oops. That looks like this. Okay, I'm really bad at drawing this. Okay. So if the particle has very little energy, it will be either here or here or here or here or here, right? So the translations are discrete. However, if the particle has a lot of energy, it will be like your car driving on a bumpy road. You just do this and pass through. So now it will explore something continuous. To make sure that it's a truly honest to goodness discrete hopping, one thing you could do is you could make this potential go to infinity. Right? This way you can make sure that the particle is stuck in one of these guys. Now, if you take this lattice, this has discrete symmetry. What I'm drawing is the potential, right? The potential V of x has the property if it's sign, for example, that is symmetric by shift by 2 pi. So this also has lattice symmetry, discrete symmetry. However, for simplicity, because I only have 20 minutes, I'm going to take this problem and try to solve it, right? Again, the next level of the disaccharide does this, and this is what you mostly deal with if you take solid state physics. Next, how many of you guys have taken solid state? I guess none. Oh, you have. Okay, good. So solid state, you just go to the next level, you take this. All right. So we're going to be talking about this setup, where the particle is stuck in one of these. You could superpose them, right? Now, if these were harmonic oscillators, they're not harmonic oscillators, but they will have a spectrum. As a matter of fact, like you could come up with all sorts of things. You could think of this as an infinite well potential that you attach to some sort of harmonic oscillator down here, right? You could do some sort of approximations. Or you could think of this as a very, very narrow infinite potential well, another narrow potential well. Looks like a, okay. Good. So now there is a unitary transformation. Oh, sorry. Now the state that is stuck down here is going to be, well, there will be an energy eigenkette of x prime, right? X prime is like this continuous x variable. And a translation, a true translation, will do this by L. Now, potential as an operator, V of x as an operator, under the action of translation is left invariant, because that goes to V of x plus A, and that's same as x. A is lattice spacing. So if the Hamiltonian P squared over 2m plus V of x, these lattice translations are symmetries. They commute with the Hamiltonian, right? They're simultaneously diagonalizable. The T of A is unitary. Its eigenvalues are phases. We did this on the board last time. Why? Right? As I said, now consider the case that is what I was trying to describe. Say simple harmonic oscillator and then infinite potential. Well, so actually, no. let me not do that. Let me make this so something like this, so that you effectively only explore the ground state. The highest energy states are really high up. All right. I apologize for the notation, but this is also standard notation. The ground state of the kth or nth site is right at ket n. This is not the nth level of this. This is just nth site, the ground state. Right? Hamiltonian, this is an energy eigenstate. It has energy E naught. Clearly, this state is these eigenkets are highly degenerate. Right? What's the degeneracy? Infinite. It could sit here, it could sit here, it could sit here, they all have the same energy. Right? Good. Hamiltonian and translation by lattice amount commute. Well, let me write it this way so that it's similar to a theorem I discussed before. However, Hamiltonian is highly degenerate. Therefore, energy eigenkets of Hamiltonian will not be translation energy eigenkets necessarily. Right? Ket n, the particle being here, sitting here, for example, is an energy eigenket. However, it's not a translation eigenket. Why? Under translation, it moves here. Right? Is that clear? The second part of that theorem says that even though energy eigenkets of Hamiltonian will not be translation eigenkets, but there will exist superposition, linear superposition of degenerate eigenkets of Hamiltonian that would be translation eigenkets. Right? Now, can you guess what those look like? All right, I'm going to pause here. Can you guess what they look like? That'll be impressive. You guess it. Well, it's not complicated, but you're a really good physicist. You can see it. So first thing, it has to be superposition. Yeah, exactly, with a bunch of CNs. Now, what are the CNs? What should the CNs be so that it's an eigenket? So far, I'm just following the theorem. Let's act on it with T of A. Well, okay. Now I'm not going to give you the answer. I'm going to pause. Now, can you? So that was first half of it. Can you guess the second half? What are the CNs? If there's zero, the ket would be zero. Very okay. That's another level of complexity. Yeah, the normalization is an issue, but let's ignore it for now. Let's ignore it for now. Indeed, you're absolutely right about the normalization being an issue. So how does TA act on, and what does it give you? It gives you ket n plus 1. Right? So if I put this to be independent of n, 1, is it an energy eigenket? Is it a translation eigenket? It is, right? As a matter of fact, more generally, I can pick it to be this. So I can pick them to be e to the power of I n phi. Phi or theta. Theta. I call it theta. Theta between 0 and 2 pi or minus pi to pi. Now, let's work out whether this is an eigenket. Is it an eigenket of translations? Can you see it? It is. Can you see it? So T of A acts on this. It gives you sum over n in z, e to the power of I and theta. Let me show it on the board. N plus 1. This is an infinite sum from minus infinity to infinity. You can shift it, and it doesn't care. So define a new variable n, send n plus 1 to n. So this becomes, let's get n. What is this? This is e to minus I theta, sum over n. Oh, this part of the chocolate doesn't work. Which is e to minus I theta, your initial state. So this is a translation eigenket with eigenvalue that's a phase. I promise you guys it will be a phase because it's a unitary. Just eigenvalues are going to be phases. Yeah.
Is n more level of H corresponds to the same?
Sorry, is what?
Is n more different energy level of H?
No. N's are all vacuum degenerate vacuum. It's about the particle. Imagine this is like infinitely deep. So the lowest energy is here that has energy E naught, and the first level is so high up that we're going to ignore. Right? Now you have infinite such things. Right? This is one energy eigenket of the whole system, Hamiltonian. So is this one. So is any other one of these, right? There's a question. Ooh, exciting. Infinite superposition. Yes, correct. You've seen infinite superpositions. Right? What's the Hilbert space of a particle on a circle or a simple harmonic oscillator? It's an infinite dimensional Hilbert space. So we have infinite superpositions. That's fine. Yeah. As long as it's countably infinite. Well, for this course, we also talked about superposition of uncountably infinite, right? We talked about superpositions of things like this, right? Yeah. Psi of x prime, right? That's what it was. Do you remember this? This is just phi. I acted on this by a resolution of identity in X spaces. Good. This chalkboard is really awful. All right. So finally, I'm gonna summarize by saying that we went over 3 discrete symmetries: parity, time reversal, and lattice translations. They are all they're symmetries. They all correspond to groups. All symmetries generate groups, and the group for parity and time reversal was Z2. Lattice translations was Z. They parity and lattice translations and all other symmetries you've learned about are going to be unitarily represented on the Hilbert space that will correspond to unitaries. However, time reversal is an exception at this level of quantum mechanics, which is anti-unitary, right? What other symmetry transformations have you learned about? Almost every aspect of the course was about symmetry transformation. There was translations in space, translations in time. Translation in space gave you momentum, the first part of the course. Translation in time gives you dynamics, Hamiltonian, second part of the course, right? Rotations, symmetry, give you angular momentum, part 4 and 5 of the course. Part 4 of the course. Part 3 was about density matrices. That was a little bit different, right? So we worked a lot with symmetries. The whole foundations of quantum mechanics, modern in our understanding of it, essentially relies on symmetry transformations. So just a general lesson for you guys, no matter what your field of study is, if you're a physicist, you are looking at a new system, first thing to do is identify the symmetries. That will save you time, headaches. First thing, looking at anything, first thing you have to identify symmetries. That's just a suggestion. You don't have to, but I recommend. All right. Are there any questions? So we've reached the end of this course.
I do have a question.
Oh, there's a question. Can we say anything about conservation laws for discrete symmetries? A beautiful question. Okay. Let's think about what that question means. We made a statement, or Emmy Noether made a statement about conservation laws for continuous transformations. What was that statement? The statement was that the generator of a continuous transformation commutes with the Hamiltonian, therefore is conserved. Good? Here is a discrete symmetry. At least at the level of this course, there's no generator of an infinitesimal transformation, right? So at this level, it's unclear what would that mean. However, the story is very interesting and fascinating. And I would even say that the interplay between discrete symmetries and continuous symmetries still remains an active area of research. It's very surprising that continuous symmetries are so, well, there's a class of continuous symmetries called Lie groups, and they are very nice and beautiful and easy to study. For discrete symmetries, it's a little bit trickier. Have any of you guys taken group theory? Group theory is precisely a study of symmetries in different systems in nature. The discrete ones I usually don't know anything about unless they're relativistic. All right. Any last questions about this part?
I have one.
Yes.
What is the physical meaning of the superposition of all of the lattice sites being a phase?
What's the physical meaning of this ket I wrote down?
Yes.
Okay. The physical meaning of that is that let's take theta to be 0. What's the physical meaning of that? It's a translation invariant state of the lattice. Right? What's the physical meaning of the ones that are eigenkets with a phase? I'm just going to say a word and move on. This is discrete Fourier transform. Learn about it. It's fun. This is really nothing but discrete Fourier transform. The 0 mode in discrete Fourier transform is the invariant mode. Good? Any other questions? So in this course, we started by talking about, I'm gonna do the, I'm gonna do the review afterwards. So are there any questions, last questions from here? Then we can discuss a little bit about the problem solving session and how I want to approach it. If not, let's close this. But you guys please stay online. We just want to discuss very quickly. We're gonna go to the room, well, whoever wants to come, 234. I should not rely on memories in physics. Wow, I got it right. Wow. So yeah. Yeah. Say it again.
Marked by label N, any adding cat for some operators except for
Depends on the details of your system. At this point, no. Thank you. At this point, no. But depends on the details of your system. You're asking if the system has other charges. Okay, sorry, we'll come back to this. So we're gonna go there. I'm gonna try to connect to Zoom. What I can do is up to you guys. I was gonna review every section of the course for like 4 or 5 minutes, very high level, and then open for your questions on that part, that section. And then we'll discuss it, solve problems. I'll probably use chalkboard. Is that better, or is that I can also use the iPad? Chalkboard, that was my thought. All right, so I'll try to set up the chalkboard. We'll see how it goes. Thank you so much, guys. Yeah. I don't know what 234 is. I don't think so. No. It's a proper classroom. Yeah. All right. I'll see you guys in a bit. I believe so.
Are you recording?
Recording this? I just did.
No,
If you want to. Yeah, sure.
just because I'll be late.
Yeah, sure. That's fine.
7
That's fine.
meetings.
That's fine.
session right now.
Yeah, it's right now. I have exactly until
Also set up my laptop.
Usually iPads have better quality of
Yeah.
your camera. I think so. Can you tell me how far?
Yeah, this must be 6 feet.
Oh, right, so it's only you should probably know on the exam, because there's been two things about this now, it's like you. Basically,
This is possible.
using the raising and lowering operator on S.
Here we go.
Well, and
Alright.
then you make your JX and JY from like, adding, subtracting, the raising and lowering. And then basically like the JX on so-and-so state to so-and-so state. What elements of the matrix and then the
I also get some chalk.
Sure. Basically like going from operator like in the lectures, you have expressions and operators in terms of and then you're given an expression for y, so it's just kind of do this, there is this one twice, and then it's not. I just try I suspect from about the group theory stuff, you kind of diverge.
Yeah.
I'm expecting. I don't even know if we passed this course until like, we're already done with all of our courses 2 years later.
Okay, people online, can you hear me?
Yes.
You can see this far, even further here.
Yeah, that one's right.
The other line is down here, right?
No,
No?
further to the left.
How about now?
Further. Like at the chalk box. At
Yeah,
the
I
box
think-
of chalk.
This is another solution. Good.
Yeah, there you go.
All right. So, this defeats the purpose because I want to go over things on my iPad. How do we do this?
You want me to join and then just shoot my camera that way?
Try please. See if I can log in here. I also could go from memory, but it's too complicated. Yeah, let's do that. Let's do that. All right, while we're waiting to set this up, how are we gonna do this? I can start talking. Well, my notes are here, but and then for a couple of minutes for each section, and then we ask for questions. Good. Can you connect to? While we're waiting, actually, until we figure this out, does anyone have any questions? Can you reach? Yeah. Any questions? We can start with. Could be anything. Thanks so much for doing that. No? Yes.
So since the book's allowed, can we put little book marks in different sections?
Sure. Yeah.
Can we print out the other notes That aren't the textbook notes,
No, I do not.
like
no.
the lectures that we use for extra. You know what I'm saying? No.
Yeah, so if people have questions, please remind me to repeat the question for people online. So the question was that, can you bring notes, other notes, something besides the book? The answer is no. You probably don't need anything really. You probably don't even need to use the book, but if it helps, have it. I don't mind, I don't care. Is it helpful if I give you a equation sheet?
Yes. Yes.
All right, I'll try to remember that to make an equation sheet. No, it's okay. It'll probably be, but it's okay. There's not much else to do. All right, any questions?
Can we get, will we get the equation sheet on, was that an agreement to the equation sheet or?
Yeah, I'll make an equation sheet. I don't think you need it though. Like every equation, I'm just gonna copy from Sakurai. So I don't know how useful it would be for you guys.
So like we don't have separate. So like, are we supposed to like print out
Yeah, so if I have one copy of it, and we could just, if people have copies, if you don't mind, we could just circle them around. I don't think you would need it.
Doesn't matter, second and third edition.
I don't think so. I don't really think so. The exam is simple. The exam is easy, I think. I did my best, okay?
Okay, yeah. Use this mic instead.
Yeah, well, sorry, let me make you host, because otherwise. Sorry, what is the account?
Don't share it. The bottom one.
The bottom one, yeah. Make host. Okay, so now I leave. All right, very good. We solved the problem. Can you guys still hear me?
Yes.
Okay, awesome. Listen. Oh, this is even has a wider. Okay, good.
There we go.
All right. The only thing is I will definitely curse. Okay. All right. So
Can we move this a little
I'll
bit?
do this very quick.
Can we move this just a little bit?
Okay.
Just a little bit.
Oh, actually, it could come even further. No, it doesn't help that much. All right. So part one, section one was about quantum states observable in Hilbert space. This is such a bad word. Observable in the Hilbert space. All right. We started, I'm not going to talk too much, but if there is a part that you want to elaborate more, I will. That's better, right? So we started by motivating using two experiments, the double slit experiment and the Stern-Gerlach experiment. Stern-Gerlach experiment was about silver atoms going through silver atoms have this intrinsic quantum property called spin, and we were rotating them or measuring various components of the spin, right, a vector. And the double slit experiment was about there was a source that was shooting particles, there was a double slit, and here we had a screen with some sort of a counter that was measuring the probability of receiving a particle here, right? There was interference pattern or no interference pattern depending on whether we were observing these or not. What were the observations that got quantum mechanics started, I guess? Historically, that's incorrect, but anyway. Certain observables are inherently discrete. They are quantized. We also saw whether we measure different things will affect the future evolution of the state. We saw that it's impossible to simultaneously measure all observables, right? So these were the important punchlines. And there were, in particular, compatible observables. These were the ones that we could simultaneously measure, and then incompatible observables that we could not simultaneously measure. The incompatible observables satisfied uncertainty relation. So we'll get this was the double slit, and the Stern-Gerlach was silver atoms that we were sending into different measurements of SC, SX, SC, for example, depending on different sequences. We realized that, so classically, there is no spin, but if you think of it in analogy with angular momentum, you would think of it as a three-dimensional vector. Except that a three-dimensional vector, when you look at different components of it, it would not come out to be quantized. It would not come out to be, you would have cosine and sine thetas, right? Whereas spin was this intrinsically quantum object that was quantized. It was either up or down. Didn't matter how you rotated things. So this is a three-dimensional vector, but we realized that if you want to model spin, what you should do is you should use a two-dimensional complex vector. This is a three-dimensional real vector, and we model these using two-dimensional complex vectors, and the space of such things we call the two-dimensional Hilbert space of a qubit. Then we use this notation. This is conventional. Sometimes we wrote it this way. Sometimes I wrote it 0 and 1. They meant the same thing. These were ket vectors, right? So we had the operation of dagger, right? It was sending some ket to a bra, right? And this operation will take the complex conjugate as well. So this dagger thing, acting on the vectors is like that, acting on operators, it's transpose followed by complex conjugation. The order doesn't matter, right? So we modeled observables, things we could measure by permission operators. So these are operators that satisfy this, right? So they're equal to their transpose complex conjugate. These were observables. Then what else did we say? We talked about the norm of, so there was the inner product of two vectors, which is it's pretty clear what it is, hopefully. So this is the inner product was a generalization of an overlap from, so this was like three-dimensional vectors. These are two-dimensional complex vectors. Now that you know that this is the SO3 group, this is the SU2 group, back then we didn't need to know these things, so we didn't talk about it. We talked about the notion of eigenkets and eigenvectors, an eigenvalue problem. If you had an observable, means self-adjoint operator, let's go with the Sakurai notation. A ket or a vector, a ket is a column vector, right? And a bra is a row vector, would be an eigenket of an operator. The operator is a matrix, a diagonal matrix, 2 by 2, for example, acting on this, if it satisfies the following equation, and we were labeling, this is called an eigenvalue, and this is called an the object that solves this equation, the vector that solves this equation is called eigenket. We had the notion of a projection. Hopefully recall what it is, self-adjoint, a Hermitian operator that scores to itself, right? Give me an example of a projection. Exactly. So let's go with Sakurai notation K prime by 5. All right. Then we had an important theorem that said the eigenvalues of Hermitian operators are real, and the eigenvectors with distinct eigenvalues are orthogonal. When the eigenvalues were not, if you had two vectors that had the same eigenvalue, we would say that there's degeneracy, right? Good. Any questions here? Actually, this is, I should not just go on a monologue. This is to help you guys. Are there any questions up to here? Actually, let's do it this way. Or I can finish part one and then section one. No, let's pause up to here. Are there any questions that are related to this up to here, what we had from homework, from anything? So what most quantum mechanical calculations would be are going to be solving eigenvalue problems, right? Often what we're interested in, as you know already, is this Hermitian operator is Hamiltonian, right? And these eigenvalues are energies. Solving for, and then we call these energy eigenkets or stationary states. And we solve that, we call that, for example, the time-independent Schrodinger equation. Is this helpful at all, or? Yeah, okay.
Yeah, this is helpful.
Okay, good. Thank you. All right, good. Feedback is good. All right. Then we had the notion of compatible operators and incompatible operators. These are the observables that we could measure together simultaneously and we could not measure simultaneously. Give me examples of such things. For example, SV for the qubit. What other operator is compatible with this? S squared, yeah, which is Sx squared plus Sy squared plus Sz squared, right? For the qubit, these S's, this SCXY, SZ were the Pauli matrices, right? So, yeah, so let me not jump around. So let me just first say what I was gonna say. There was one very crucial result about incompatible operators. The thing that you need to know about incompatible operators is that based on the fact that they don't commute, they have non-vanishing commutator, they satisfy uncertainty relations. So what is an uncertainty relation? It says on the right-hand side, it says, so you have two Hermitian operators. This is important. These are observable, right? On the right-hand side, you have this. Of course, if this is the commute, this is zero. We don't get anything non-trivial. So on the right-hand side, you have the fluctuations. This is true in any state. Good. So this notation, let me elaborate what it means. So first of all, what is delta A? It's A minus the expectation value of A. Delta A squared is the same thing squared. And when I write this, I mean in some ket sign. So the ket is suppressed in this whole notation, but it holds for all vectors in the Hilbert space. Now, in the case of simple harmonic oscillator, perhaps the most important example that we work with, there were kets that saturated this. What were they called? Coherent states. Just yell loud, even if it's incorrect. We all learn something. Sometimes I learn as well. All right, good. We talked about if plus minus are the eigenkets of SZ, then we saw that eigenkets of Sx are 1 over square root 2 plus minus minus. And if you write these as these vectors, this would be 1 over square root 2, 1 plus minus 1. And then the eigenkets of Sy are going to be, hopefully you recall what they are, right? There's an I in there. And then we saw that the fact that we needed an I in quantum mechanics to explain interference. So we had these matrices. This is Sx, right? So it's H bar over 2 plus minus plus minus plus. I'm not going to write this anymore. So this is sigma. Oh, Sx, right? Then we had sy, which was minus I, thing in my notation. Yes, and then sz is half 1 minus. These guys are Pauli's up to h bar over h bars. They're called Pauli matrices. They satisfy the following commutation relation. Si and Sj, I and j run from x, y, z. Sometimes I say 1, 2, 3. Is I h bar s k epsilon I j k. This is a totally antisymmetric tensor. Is that clear? All right. There was another useful relation, but it's not fundamental at this level of this course. The anti-commutator of these guys is h bar squared delta I. Actually, there's something really neat from this expression. Let's look at this. I wish I had the orange thing to wrap around. I'm doing iPad, I'm bored in my head. So this is x squared plus sy squared plus sc squared. If I put sx squared here, what do I get? I get h bar over 2 delta xx. If I put sy squared, I get h bar over 2 delta yy. If I add sx squared plus sy squared plus sz squared, which is the whole thing is s2, I get half h bar squared identity. Over 4, sorry, I messed up. You just have to add them up. It's proportional to identity. You get 3 over 4. So do that calculation. They don't all add up because they don't count. All right. Any questions? Yes.
This is maybe a very specific question. I remember going through derivation, certain relationship.
Yes.
That's presented exactly right. And they, I think the profit term is the right-hand side of that.
Yeah.
Sign, and actually that sort of confuses me why they do that, because then when you break it down in the current states, then I think it's sort of meaningless to call them saturating conservative.
Let me explain. What you start with to derive this, we did this on the board, is an equality. To get an inequality, you drop a positive term. The states that saturate this inequality are the ones that the positive term vanishes. Those are great questions, by the way. Any other questions? By the way, we also talked about unitaries. What was the physical picture of unitaries? Well, we were brainwashed by the last lecture, which was about symmetry transformations. But if you have, okay, let me explain this because I got a lot of questions about this, and I think probably most of you guys don't know this fact about linear algebra. If you have a self-Hermitian operator, right? It could always be written in the following form, where D is a diagonal matrix and U is a unitary. What does this mean? It means that we're diagonalizing the matrix. So this is the matrix elements of this guy are the eigenvalues of it. So when we write, this is the principle we use to write the matrix this way. What these are, this is a collection of the eigenvectors. Definitely do this for yourself, for it to click. All right, everybody's with me so far? So these numbers are real. We just said that. A unitary will change basis for you. Now, here's a fact that I think most of you guys, well, I got a lot of questions, but I don't want to say it. Anything. So if you have operator A, look at this structure. If I want to calculate A squared, what do I get? I get U D U dagger, U D U dagger. This is identity. I get U D squared U dagger. What is that? Is this matrix, these guys squared, so diagonal matrix, not squared, U dagger. What is UQ? Same thing. Same U dagger, these guys Q. What is an arbitrary function? So if you take something like this, let's say alpha 0A plus alpha 1A2 plus alpha alpha 0 identity plus alpha 1A plus alpha 2A2 plus alpha 3A3 plus da. You see how it goes? What is that operator? No, depends on alpha. Right. But what that operator is U alpha identity plus alpha 1 diagonal, alpha 2 diagonal squared plus da U dagger. So if you have an exponential has a series expansion like this. Any function that has a series expansion, if you want to evaluate it, one way to do it is to take A squared, take A cubed, and look for structure and resummation. We did that sometimes. Another way of doing it is diagonalize it, exponentiate this, apply the unit terms. Right? When you go on Mathematica and type exponentiate math x, that exponentiate the matrix. Mathematica doesn't try looking for structure, guessing what it looks like to resum. It does this. Good? By the same logic, any function that has series expansion could be written this way. So now you know what it means to talk about something like this. Right? Do you see down here? Sorry, is it clear? Okay, I'll try not to write too far down. All right, any questions?
I have a question. For SZ, is it H bar over 2 or 1 over 2?
H bar over 2, thank you.
Okay.
Yeah. Otherwise, you don't get this. The set of eigenvalues of an operator are called the spectrum of the operator. All right. Good. Any questions? Please do ask questions. I can try to remember what kind of questions I got throughout the semesters and go over them again, but it's better if you do ask questions. I'm also happy to, if you pick one of the homework problems, then we'll do it here. But it's better if you pick a one that most people want to do, because we can solve. We don't have limited time. But if there is the homework problem that most of you guys want to know, I can do it quickly on the board. All right. So I'm going to speed up because otherwise I won't get anywhere. We talked about the eigenfunctions, wave functions in position and momentum space. This is the wave function in position space. We talked about the resolution of identity in any basis. We talked about position operators, so this was the notation. Let's just know. These are eigenkets of the position operator. We talked about the momentum operator. What was this? It was minus IH bar del X prime. Actually, that's not right. That's not the nicest way of writing it. Let me write it up here. So P X prime psi is minus IH bar del X prime psi. crucial, we had this relation. 1 over 2 pi h bar exponential of minus ix prime p prime over h bar. What was this useful for? Let's just remember this. What was this useful for? So in one of your homework problems, well, there are a gazillion different ways of doing those homework problems. But there was one that was, I gave you a Gaussian wave function, or any wave function as a matter of fact, and I asked you to evolve it with a free Hamiltonian, right? How would that be? So here is the wave function you're given. It doesn't matter which one it is. How would you do it? You insert a resolution of identity in the p prime basis. I think there's 2 pi h bar down here. I don't remember what my convention was. Do check. Yeah, that's what it is. X prime, p prime psi. Now, you know what this is. Why does this help? The reason it helps is that if you want to evolve this in time, this is x prime e to minus IH t over h bar, and h for the free particle is p prime squared. So e to power minus IH t will give you, here you could just take it out. It will give you e to minus something p prime squared over blah, blah, right? Now you have this, you have an integral, you have explicitly every element of it, you could do it. Yeah.
Is this one set to number 4?
I don't know.
Sorry, it's where you said use the overlap x prime p prime and 1 over 2 pi h bar exponential.
Yeah, I was probably, yeah, sounds like the right setup. But I'm telling you the general idea. The general idea is that, like, you have a wave function, and you want to evolve, or you want to stick in the middle some operator. That's not an eigenkit of, this is not an eigenkit of it. You put in there a resolution of identity of the eigenkit of that operator. So you find your expression as an integral. Is that good? Right? That's a general principle. That's how we use integrals to evaluate those expressions. Doesn't have to be free particle, doesn't have to be x and y. X and p could be sigma x and sigma y. They also have resolution of identity, right? Is that good? Is that helpful? Sorry, let me make sure. I can go over that problem if you want as well. But the basic idea is this. Let me just repeat that. You have something like this, and in the middle, you're putting an operator. If this operator was x prime something, then you could just evaluate, because it's an eigenkit. But if it's some other operator, I don't know, A, the way you would evaluate it is you would put a resolution of identity of A here, and then you would need to know the overlap of x prime and A prime. Then you could write it as an integral or something, right? What takes you from the x prime to p prime, x to p basis is Fourier transform. I'm not going to write it on the board because we don't have much time, but I just want to repeat that. It's just Fourier transform. You have the explicit expression. We talked about Gaussian wave packets. The Gaussian wave packets where what is a Gaussian? It's exponential of something that is, so it's a Gaussian x is an exponential of minus something that is bilinear in x, like alpha x plus beta x squared. That's a Gaussian, right? So for example, the Gaussian wave packets let me call this, I don't know, I think I called it D. Exponential. You can see this far? IKX prime.
Yes, we can.
Thank you. So this is second order in x prime. This must be minus sign. Why? Because otherwise it's not score integrable. Right? This is a phase. It doesn't matter in the probability. If you look at the probability density of this phase plays no role. It plays a role in the overlaps. And this, how do I find this? Gaussian integrals, the fact that the state is normalized. Now, what does this look like? Ignore the phase for a second. What this looks like, this is just intuition. It's some wave packet. Oh, actually, let me, I don't know how comfortable you guys are with Fourier transform. Let me just tell you some very basic stuff that every physicist needs to know. So the Fourier transform on a line, there are a few things that you need to know. If you have a sine wave e to the power of I kx, I px, what's the Fourier transform? And this is in the x space. What's the Fourier transform of this? It's a Dirac delta function. So let's call it P naught. Yes. So it becomes in the Fourier space, it becomes a Dirac delta function P naught. Okay. The idea is this. Now take a Gaussian. A Gaussian is an approximation of a Dirac delta function. The Fourier transform is also a Gaussian. But Fourier transform does this. The wider this guy is, the more peaked this guy is. It completely delocalizes things. If you make this absolutely sharp, like a Dirac delta function, then this doesn't localize at all. It just goes on forever. Right? This is an intuition you should have. So the Fourier transform of Gaussian is Gaussian, but if it's peaked in X, it's pretty flat in Y and in P. All right, questions. This is all I wanted to say about part 1 of the course, and I need to speed up.
So I have a
Yes,
sort of
please.
comment, sort of a question. So what you were saying with the Fourier transform making one that's really wide in say X makes it very sharp in P, so that would then connect to the uncertainty relationships, that if you have a really high uncertainty in one, you'd have a low in the other.
Correct.
Okay.
Absolutely. That's a good point. Thank you. So that relates to the uncertainty relation of X and P. Right? But uncertainty relations, we wrote them for 2 arbitrary operators. The uncertainty relation of X and P, so what is it? The right-hand side had the commutator of AB, in this case, commutator of X and P, which is IH bar. And then there was an I, forget that, because we took the norm of it. So H bar squared on the right-hand side, there's a factor of 1/4, right? What H bar over 4 tells you about the uncertainty relation in the example that you were giving, right? Between the, so if you squeeze one of them, so that delta X squared actually is exactly a measure of how wide this is. The larger delta X, what is delta X squared? I don't know what you guys call it. It's the variance, or the variance. It's fluctuations. That's what it is. All right, good. Any other questions? That was good. Thank you. Do I need to go over the postulates of quantum mechanics? It's a lot of formal talk. I'll skip that unless there are questions. You can always read them. You can always ask questions. How about the description of a measurement? That's perhaps an important part of. Well, actually, I'll comment one thing about the about tensor product, because I want to make sure you all get tensor product. But measurement. Are there any questions regarding measurement? We're good. All right. You guys know what expectation values are, right? I at this point I hope you do. If you have 2 orthonormal bases, we had the theorem that they're always related by unitary. Is that intuitive? Is that clear? In a Hilbert space, that's a complex Hilbert space version of the fact that every basis in R3 is related to any other basis in R3 by a rotation, SO3 rotation. Okay. It's all good, it's all good. All right, the density matrix. Are there any questions about the density matrix? I think, yeah. Because that's not in the textbook much. So please do ask questions. A density matrix is a positive operator that has unit trace. Does everyone know what a positive operator is? A positive operator is an operator whose spectrum is non-negative numbers. So in particular, it has to be Hermitian, right? We had different characterization of a positive operator. One of them was that every positive operator could be written as Q dagger Q. Another one was that every matrix element, every expectation value of a positive operator in any state is non-negative. Is that intuitive? Okay. Why were we using density matrices? Density matrices are ensembles that describe a system. It was, if I have so ket states, we call them pure states. If I want to describe a system, which with probability 1/3 is in ket 0, and with probability 2/3 is in ket 1, I would describe that using a density matrix. What is that density matrix? It's third ket 0 bra 0 plus 2/3 ket 1 bra 1. Right? Why did we need density matrices? Because of entanglement, but I'll get there. It's an inseparable part of description of quantum mechanics. But given a density matrix, what's the expectation value in a density matrix? So I have a density matrix rho and I have an observable A. How do I calculate the expectation value of the operator A, observable A in density matrix rho? Trace of rho A. All right. All right. Questions? I'm going to switch to quantum evolution. Quantum evolution. Any questions up to here? I would rather you guys ask questions. Are there any questions? So we started the discussion of dynamics with an analogy with classical physics and the Poisson bracket, right? And then we said there was a Schrodinger picture in which the states, so what are classical states? There are probability distributions on the phase space. What are classical observables? There are functions, real functions in the phase space. What's the classical observable, for example? X squared, or classical harmonic oscillator, or XP, right? Is XP a quantum observable? Yes or no? It's not. It's not Hermitian. So in going from classical physics to quantum physics, what we did was we replaced the Poisson bracket by I over 1 over IH bar, the commutator, with the Hamiltonian, right? So I'll not review that unless there are questions. I'll just start talking about the time evolution operator. Yeah.
Actually, back to the density.
Mhm.
So if in general we were doing an arbitrary density matrix and wanted to calculate the trace of it just to see if it equals 1. In general, would we essentially have to diagonalize the density matrix for the trace?
Very, very good. So give me an example. Let me give me an example. So how are you given the description of the density? So you want to calculate the expectation value of an operator, right? So you want to calculate trace of rho A. If you're given the description of these as matrices, just multiply them and calculate. The question is, if you only know the eigenvectors of this guy, eigenvalues of this guy, you're given it in the diagonal basis, but somehow they did not describe to you what the eigenvectors are. Because if you know the eigenvectors and eigenvalues, you construct the matrix, you're done, right? Can you do the calculation? The answer is no. you can only do the calculation if, in that case, if both of them are diagonal, simultaneous diagonal, they can. All right, regarding the density matrix, I need to say one more thing. Is everybody comfortable with tensor product? Is everybody comfortable with Schmidt decomposition and partial trace? Partial trace. That's crucial. You need to know partial trace. Absolutely, there's no way around it. You can't these days do physics without. Good? All right, awesome. Those were the parts that were not much in Sakurai, because Sakurai is out of it. All right, the time evolution operator. We talked about the Schrodinger and the Heisenberg picture. In the Schrodinger picture, evolution, there was the situation where the evolution was, the Hamiltonian was time independent. In that case, what was the evolution operator? E to minus IHT over H bar. When the Hamiltonian was time dependent, but Hamiltonian at different times commuted, what was the evolution operator? E2 minus IH bar integral over D of t of HT. Most general scenario is when Hamiltonian is time dependent and at different times they don't commute. This is where you get the Dyson series. That I can say there's a simpler way of writing it. We wrote it as a time ordered exponential. I don't expect you guys to have an intuition about time order exponentials. That takes a long time, but I want you to know an in principle way of being able to look it up and do calculations with it. You need to understand the concept. Why is it that it doesn't make sense to add HT1 and HT2 and just write exponential? It does make sense, but you're making a choice. Because they don't commute. Is that idea clear or not?
Could you write down what you just
Yes,
said?
yes. Yeah, please do ask. Thanks. I'll assume you know it if you don't ask. Thanks so much. So here. What is this? This is sum over AB to the power of n over n factorial n from 0 to b. Right?
No, I'm sorry. I meant, could you write down what you said before? I think it was with the
Very good.
time evolution.
Just write it. You could look it up in Sakurai, but here, let me just write it up. So time evolution operator, when it's Hamiltonian time independent, is this minus IHT over H. Of minus I over H bar, integral of D of t, H of t. So this expression looks like this, right? You're adding two operators at different times. When your Hamiltonians at different times do not commute, that's like exponentiating in this when B and A do not commute, right? Here, there's something important going on. If you expand, if this is the definition of it. So expand one of these terms, for example, AB plus 2. Is this, right? Plus AB plus BA. You have to be careful with the order of things. If what you were adding was H of t equal 1 plus H of t equals 0, H of t equal 1 has to be always applied after t equals 0. Whereas this exponential will reverse or include terms that have reverse order. That's why the Dyson series is complicated, and that's why you have to time order. Is that good? Question was asked.
Yes, thank you.
Sure. All right. Simple harmonic oscillators. Any questions about simple harmonic oscillators? Yeah.
There was a question in the homework where we had the simple harmonic oscillator, and then there was a force which was minus q fx.
Awesome. All right, let me do it for you guys. I'll just give you the idea, right? Finish your question. What's the question?
Yes, I had like a lot of trouble with like using the vector functions and.
You
yeah.
didn't need to. You didn't need any of that. All right, here's the trick. Well, you could do it. You could do it that way. It's perfectly fine, right? You could just solve the Schrodinger equation and try to solve it. But what is it? The Hamiltonian is good job. P squared over 2m plus, correct me if I'm wrong, was it, how did you write this? Did we write it as a half omega squared x squared, right? That's how we wrote it. Let me just say it in the most general case. If you add to this a term that is linear in x, which is the case of that problem, you could try to solve this Schrodinger equation again from scratch. Or you could play a trick. What is the trick? Look at this and complete the square. Define a new variable y, which is x plus something. That something is constant, so your p's don't care. You write this as p squared over 2m plus half omega squared y squared plus a constant that you could calculate. This whatever comes out of the completing the square, right? Now, if you solve this, you know all the wave functions of this. This is a simple harmonic oscillator. It has the exact same eigenkets after replacement of y by x. The only thing that's happened is that eigenvalues are now shifted. That's it. Gaussians. Again, the rule is that if you're dealing with Gaussians, things are easy.
What's the shift direction? Like if you add a constant term, you shift energies down, you shift energies up.
Depends on your constant. If it's
Sorry,
positive,
if it's a positive constant,
it shifts up. If it's negative, it shifts down. Yeah. There was some magnetic force here, right? There was a particular value. I don't remember was up or down. But it depends on the sign of alpha, for sure, right? But it's hopefully clear that when you solve this differential equation without this, you have solved a whole class of such things. Any other questions? Okay, Baker-Hausdorff-Campbell, BCH. Do I need to go over it? Do I need to explain it? Yes, okay. Baker-Hausdorff-Campbell is when you have two, what was the form that we gave you guys? I think we gave you guys. Okay, I'm going to write something. Actually, let me check to see what's the form I gave. I gave you the explanation. Imagine IG minus IG. Is this this in general comes up in quantum mechanics all the times. Why? For G self-adjoint Hermitian. Why? Actually, let me make this comment. If I have a Hermitian operator, if I multiply by I, what kind of operator is it? Anti-Hermitian, right? An anti-Hermitian operator is the one that when you take the dagger of it, it's minus it. So if I put an I here, take the dagger of it, you pick up a minus sign. If it's Hermitian, this is anti-Hermitian. Exponentiate an anti-Hermitian operator. What do you get? A unitary operator. Every unitary operator could be written as an exponential of I, a Hermitian operator as well. That's always the case. These are very important facts. You could just derive them using linear algebra. You have all the pieces to derive these, but I'm just telling you. Good. So now it should be clear if the spectrum of G is, I don't know, like a bunch of numbers A1 to AN, and G's Hermitian. What are these numbers? Real. What's the spectrum of exponential of EIG? Exponentiate every single one of them. What's an exponential of I, a real number? A phase. I've been saying that over and over again. So eigenvalues of Hermitian unitary operators are phases because they're exponential of I, a real number. All right, I'm gonna write what a coherent state is. Do I need to? Yeah, okay, there are questions here. Oh, I did not finish this. Thank you. So this is, I think the form I gave you is this, right? What is the form I gave you of BCH? Yeah, I think this is the form I gave you. This is Y plus I, commutator of G and Y, plus I squared over 2, commutator of G and G of Y, and the rest continues. These are called nested commutators. If G is H, what is this commutator? I, commutator of H and Y is
What is Y?
anything. What was the Heisenberg?
Is it I, E, I, J, K, H bar?
What is the Heisenberg equation? Heisenberg equation says d dt of any operator Y is 1 over IH bar, commutator of Y, and H. So this is related to time derivative of Y if this is H. So what this is that if this were H, this is a time evolution in the Heisenberg picture. This is a series expansion of it. This Y plus I del Ty, Y plus del Ty plus half del T squared of Y, and so on and so forth, times T squared. There's a T in it. So this is just a series expansion of the function. All right, is that good?
So are you supposed to use this as like an approximation? Like you go up to a certain nested commutator, then you stop, or
If there
supposed
is
to
a
play out
small
somewhere?
parameter here, let's say this is Hamiltonian time, and this is time evolution, and you are interested in knowing the evolution of operator a short amount of time, that's what you could do. However, if this is not small, you would have to resum the whole thing. And we did this sometimes, right? For rotation operators, we resum. So if there is no sense in which this parameter is small, you can't cut it off. It's like series expansion, right? What's the point of series expansion? You can cut it off if you have a small deformation, or if you're lucky, you just resum the whole thing. We're lucky a lot in this course. We resum the whole. All right. Is that good? Good. Yeah. Any other questions regarding this? Okay, I wanted to make a comment, but I forgot. Is everybody comfortable with coherent states? If not, go back. I'm happy to explain again. Go back and look at them, what a coherent state is. There are various ways to define them. You could define them as states that saturate the uncertainty relations. However, that's not the most elegant way of defining them. Another way of talking about them, you could write them down explicitly. We wrote them down explicitly in the simple harmonic oscillator in terms of the energy eigenstates. Do you remember what the coefficients were? they were the square root of the Poisson distribution. Poisson distribution is important in physics. I'm not going to go on tangents. Another way of defining a coherent state that you should check is that they are the eigenkets of the lowering operator, annihilation. All right. Then we talked about the physical significance of the wave function. This part of the course was kind of detailed, so I'm not going to write much on the board unless you want me to. We separated the norm of, so the wave function is complex. There was a norm of it, and then there was a phase part of it. The norm of it has the interpretation of the probability density. Then we chased after the interpretation of the phase. We saw it was related to the probability flux, right? It was the phase of it was related to probability flux. What else did we say? We used that to motivate. We took it from there, and then we talked about the classical approximation, the WKB approximation. What was the WKB approximation? Let me just tell you high level, because I think that part of the course I rushed. Let me just remind you what the WKB approximation is. You're trying to solve the Schrodinger equation with a crazy potential in space. That's hopeless. Now imagine your potential is slowly varying in space. So like the potential could be a crazy function, but at any moment in space, as you vary, it's just slowly varying. Then what you could try to do is you could try to solve it locally. If you zoom in, it looks like a flat potential. That's easy to solve. That's just a wave with a phase that oscillates by depending on your energy and the shift of the potential. The WKB approximation is an approximation that you assume the potential is slowly varying in space. We talked about this object. What was the name of this? What's the name of this? Yes, you need to.
Transition amplitude.
It is a formal transition amplitude, but there's a particular name if it's about, this is the transition amplitude for a particle that from position x prime at time t equals 0 to position x double prime at time t.
Propagator.
Sorry?
Propagator.
Propagator, yes. Propagator solves the is the Green's functions, if you remember what Green's functions are, is the Green's functions for the Schrodinger equation. We derived the propagator for free particle explicitly, right? All right, so we have 25 minutes, and I'm at the beginning of part 3 of the course. I'm going to pause for questions. Any questions, homework related to anything up to here? Actually, anything including composite. Angular momentum, let's keep that simple. Yeah.
I'm stuck on getting like the higher order spin rotation representation. Well, spin
yeah. So I commented on that earlier. What you're trying to accomplish is you have a matrix, 5 by 5 matrix or whatever it is. You're trying to exponentiate. Is that right? How do you do that? If that matrix is Hermitian, you first diagonalize it. You find the U's that diagonalize it. You find the eigenvalues. You exponentiate the eigenvalues. You rotate back. That's how you do it. Now, in the case of spin 1, you were lucky, or we were lucky, where You could exponentiate to second order. Oh, you saw a pattern that repeated. That's not the rule, but that's how you do it. Good question. Any other questions up to here? That was the point of it. Yeah.
The thing with like, is there a way to, if you add spin 1 and spin 2, you'll get,
Let's keep that for addition part of the angular momentum. Yeah, because I'll go through that hopefully in more detail. Any other questions? Up to angular momentum. Could be related to homework, as I said. I don't think I didn't give you any hard, difficult one. I think, you know, I should say that. But all good. All right. So angular composite systems. Partial trace symmetrization postulates anything. Boson, fermion, anions are not going to be in your exam. We didn't even do anything. I just said what they are. Entropy. You remember what entropy was? Von Neumann entropy. Pure state, mixed state. How do you tell state whether a density matrix is pure?
You find the purity.
You find the purity, which is trace of rho squared. And if it's 1, is pure. What if, so if you have a pure state, what is trace of rho to the power of n? 1. Right? Okay. Those are related to what's called the Renyi entropy. All right. We talked about the connection between spin and exchange symmetry. We talked about how statistics is affected. Yeah.
So actually, I think. So if we want to calculate, we need.
Yes, absolutely. Absolutely. There's no shortcut. That's a great question. And when you diagonalize it, what it is just the Shannon entropy of the eigenvalue.
Can you repeat the question? We couldn't hear it.
Oh, sorry. The question was that if you want to calculate trace of rho to the power of n, rho a density matrix. Do you have to diagonalize a density matrix? I absolutely recommend doing that. Because you might be able to do the calculation for n equal 2 or 3 or 4, but in general, for an arbitrary n, you would have to diagonalize. Good?
Yes, thank you.
Yeah, okay, thank you. Please do remind me to repeat the question if there's a question. I'll focus on not stepping on this, but it's taking a lot of background processing. All right. Bosons, fermions, distinguishable particles. They have different statistics. They have, right? We derived the distinction between them. We use equipartition, and then we saw using the equipartition, the most likely scenario, most likely probability distribution for bosons was for identical type, distinguishable particles is this you absolutely need to know for a general knowledge of physics. Maxwell-Boltzmann, right? This is Maxwell-Boltzmann. If they are indistinguishable, then in quantum mechanics they are generally particles, you have multiple particles. You could have bosons or fermions. For bosons, you had what distribution? Bose-Einstein distribution. Look it up. The distribution is different. It's important, the difference, right? And well, we will say in a second what important feature I want to point out. For fermions, the distribution was the Dirac-Fermi distribution. Importantly, bosons, because the wave function is symmetric, they could sit on top of each other. So the probability distribution had a non-zero distribution for multiple bosons sitting on top of each other. Fermions don't like each other. They avoid each other, right? So you can't put two fermions in the same state. So the distribution has no values for multiple fermions, right? It's always 0 or 1. That's it. That's all we can get. All right. So that is for that. And we get to the angular momentum. Are there any questions up to angular momentum? Oh, you asked me to record it, right? Good. I forgot.
It is recording.
Oh, it is recording. Thank you.
It's been recording since the class.
Thank you. Thank you. Oh, wow. How is that possible? Maybe it's recording here. All right. Thank you. Thanks so much. I do things I don't know. All right. Any questions up to quantum angular momentum? So I do have one regret. Next time I teach quantum mechanics, I will make sure I say spin angular momentum and orbital angular momentum a million times so that clicks. Is the distinction between the two clear? The reason I didn't use this terminology over and over again up until we got to the orbital angular momentum is that most physicists don't. But for learning the first course in quantum mechanics, I think it's good to just put it in your head that orbital angular momentum and spin angular momentum are two different things. But they're all representation theory of SU2. So once you're comfortable with it, it's pretty clear. Well, one of them is SO3, but they're related. All right, so what are representations? Do I need to review this? Well, okay. Let me write this. I have 15 minutes, so I'm gonna use this to equations on the board. If that's useful, if you find that useful. I don't like this chalk, so I don't find it useful. But all right. So if you have a rotation in 3 dimensions around axis n hat by angle phi, right? In real world, this is described by 3 by 3 matrix. It's the special orthogonal 3 by 3 matrix, SO3. They form a group, SO3. Good? On the Hilbert space, this is represented by matrix. If it's acting on a Q dit, it's represented by D complex matrix, right? Which is going to be SUD. For example, for the action of a rotation on a 2 by 2, on a qubit, this will be a 2 by 2 complex matrix. In general, it's actually this. These S vectors are the spin guys, right? They satisfy the thing I wrote before. This is the algebra they satisfy, the algebra SU2. In the case of spin half particles, S is basically sigma. Let me see, I put a no, S is H bar over 2 sigma. I think that's my notation. Right, and then the sigma are sigma X is normalized this way, sigma Y is this, and sigma Z is this. Yep, that's correct. I think I had a typo in one of my things that I corrected. Okay, now let me write this on the board. And this is probably the only thing I want to say about this part. So let's write this down explicitly for the spin. What does it look like? N hat is a unit norm vector. So it has nx, ny, and nz. And nx squared plus ny squared plus nz squared is 1. That's what it means to say n hat. If you take these matrices and multiply them by that, you're going to get minus I over 2 here, X here, and Z here, and Z here, minus NY plus NY. Everybody understands this? Then we exponentiate this, and we wrote it down. Now, how do you exponentiate this? You could either exponentiate it using term by term, see the structure of it, and recursively solve, resum. That's what we did. Or you could diagonalize and using unitaries exponentiate and diagonalize back, right? And rotate back. All right. There's not much time left, so I'm just gonna say this in words. Euler rotations were a way of making a simple convention for talking about rotation, arbitrary rotations in 3 dimensions. What was special about them was you rotate by some angle alpha around z. I forget the order I said. Is it gamma first? Yeah, around z by angle gamma, then around y, I said. Yeah, y by angle beta, and then z again by angle alpha. But you keep x, y, z fixed. Good. These are Euler rotations, and you use Euler rotations also in the representations in the Hilbert space. Why? Because in the z basis things are diagonal. That's easy. All you need to find is the rotation in the y basis, and that you use the Wigner matrices, right? All right. J squared, JZ, they commute. We define J plus and J minus as JX plus minus IJY. J plus, J minus are raising and lowering operators. They are not Hermitian operators. We wrote them down explicitly, right? We saw that representations of SU2 took the following form. They were labeled by 2 parameters, J and M. H bar is the eigenvalue of SZ, and H bar squared J times J plus 1 is the eigenvalue of J squared. Similar story for orbital angular momentum. We label them by L and M. Oh, sorry, I forgot to say. So M takes values from minus J1, we increase all the way to J. So the dimensionality of this Hilbert space, fixed J is to J plus 1, right? The lowest state is killed by L minus. The highest state is killed by L plus. That's all you need to know. Oh, J is half integer. Now, the representation theory of SO3 is exactly the same, except that you only pick the integer ones. There was a problem in your homework. What is wrong if you pick half integer for orbital angular momentum? We also gave an argument for it. All right. For what is this? What's the name of this? Spherical harmonics. You, instead of x prime, you use r theta phi. And this is YLM. Well, theta phi. These are YLMs, right? We wrote them down explicitly. The way we wrote them down was we found the lowest one or the highest one, depending on how you want to do it. The lowest or highest one had sine of theta to the power of L. I think the highest one has that. And then e to minus IL phi, and then you get the rest by acting L minus. Very impressed, I remember this question. All right, central forces and effective potential. Yeah, this part is a little bit calculation heavy, but are there any questions about that? Because I'm running out of time pretty fast. Yeah, so what we did was we took the 3-dimensional spherically symmetric case, we wrote down the Schrodinger equation, time-independent Schrodinger equation. We did a change of variables first. Well, YLMs appear there because of by separation of variables, right? And then the radial part of it, there was an effective potential. We first divided the radial part of the wave function by, or multiplied it by, multiply or divided? multiply them, multiply by r, so that it takes the form of a one-dimensional Schrodinger equation. Then we solve near r equals 0 and r equals infinity, took an ansatz, plugged it in, and solved. Depending on your potential. We solved the hydrogen atom. I think that was the only one that I really solved. And then there was a homework problem about that. All right. I have about 6-7 minutes to go over addition of angular momentum, and that's all I have left, but I want to pause with questions.
So just really a high level, the structure that material is presented in the book. If I introduce spin, you did orbital angular momentum, these two concepts have similar properties in computation relations, and then the addition of angular, you can prove these together.
Right.
And these properties.
Right. Those are all statements about groups and representations. What was special about orbital angular momentum is that you could relate the ket LMs to position basis, because L is R cross P. So you could talk about YLMs. Whereas for spin, this is a purely quantum notion. So you just have abstract Hilbert spaces and you write ket plus, ket minus, right? There's no X prime. If there were such a thing, we would talk about X overlap of X prime and plus, but that's nonsense, right? So YLMs are about the fact that this guy is actually in real, as a representation in terms of real space. Very good question. I think I did a poor job of that. Next, if I teach it ever again, I might get kicked out. We'll see. All right, any other questions?
I have a clarification on
Yes.
sort of the notation. Is J and S, are J and S the same in terms of they describe spin, but I think I read somewhere in the textbook that S is specifically for spin half, but J was for
Okay,
any spin?
that's notation, and I don't recall what the notation Sakurai is, but let me just clarify one thing. Because we are writing ket JM, it's reasonable, right, to think of the let me see how I want to say it. Okay, no, so let's put J aside. Let's talk about S. If you write down, I erase the computation. The only thing that really matters is this. Oh, here, the only thing that matters is this. You put H bar down here or not? If you put the H bar down here, then the commutator on the right-hand side will have IH bar epsilon IJK, right? If you don't put that down here and you put it something like this, right? Then this would be sigma over 2. These would be the Pauli matrices. So on the right-hand side of their commutation relation, there won't be an H bar. I think I use J and S synonymously. They're the same up until addition of angular momentum. When we got to addition of angular momentum, I used S as spin angular momentum, J as total angle. And that convention is standard. But I apologize that the convention is all over the place. I might have actually, probably Sakurai was more careful than I was, so I suggest sticking with whatever is the convention of Sakurai.
Okay, thank you.
Sure. All right. I'm just gonna quickly say this. 2-3 minutes left. There were, in addition to angular momentum, the thing that matters was that we had 2 different bases. So you're adding spin, the first spinner, say spin half, another spin half. There is the basis of the first one, tensor the base of the second one. So you have 2 qubits, right? Up, up, down, 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 up, up, down, right? This basis. The other basis is the basis of the total angular momentum. We saw, this is, the whole thing is 4-dimensional. We saw we had a 1-dimensional spin 0 mode, right? That was the singlet. That was up, down, minus, down, up, square root 2, outside, 1 over square root 2. And then there was a triplet, which was spin 1. There was up, up, that is 1, 1, down, down, that's 1 minus 1, down, 1, 0 is up, down, plus down, up. All right. Let me write this on the board as well. It's all last. So there's a unitary transformation that takes us in between the two bases. So there is this basis. This is the total angular momentum basis. And then there is the tensor product basis. M1, M2. The coefficients that sit here are just come from resolution of identity. M1, M2, J1, J2, Jm. The coefficient, whatever they are, they're called the Clebsch-Gordon coefficients. Okay? We calculated them using the so-called recursion relations by acting J plus and J minus on various vectors. And 3 points we made about them. First, by convention, Clebsch-Gordon coefficients are all real. Second, M1, M2, whatever is my notation. Yeah, M1, M2, and M is proportional to M1 plus M2, M. I'm suppressing J1, J2. J. The last thing is that when you add the total angular momenta, you find spins in this range. So when you add two spin half particles, you find the spin 0 mode, you find the spin 1. That's it. Sorry. All right, I'm out of time and I have to get going, but are there any last questions? Yes. The notes here? Yeah, sure. I'll post them. All right. Well, one last comment, and I also have to run out now. I asked the TAs to do. They promised they're going to be done doing the grading as much as they can by Sunday night. Here's what I'm going to do regarding final grade. I don't know how I care, how much you guys care, but there were some students who just wanted to write the final. That was okay with me. That's 100% of their grade. Whoever did that, that's how I'm going to evaluate you. There were, you have homework and the final. I'm going to come up with two different formula just to make sure that I'm not too cruel to students who showed progress. So in version 1, the homework has less value. The final exam has higher value. Formula 2, I haven't decided the percentages. Homework has higher value. Final exam has less value. Your grade is the max of the two. Okay? Thank you so much.
Thank you. This was very helpful, by the way.
Yes, quick.
This was very helpful, by the way. Thank you.
Oh, okay, sure. All right, bye guys. For the final exam, I'll be a little bit late to the final exam. Martin Pujansky, my colleague.